Now let's talk a little bit about validation of PLS models. There are several aspects to that. Most of all, selecting the number of components, how many PLS components to use in your model, but also checking for outliers and maybe also some sort of variable selection. We're mainly going to talk about the first one, selecting the number of components. We can talk a little bit about the outliers, but then we'll focus on finding the right number of components. One thing that's important to remember is that all these things and others depend on each other. So you cannot have a sequential approach saying first I find the outliers and remove those three, then I select the number of components, etc. Because all of them will affect each other. So you sort of have to have an iterative approach to this, finding a nice solution. That's difficult initially when you do modeling, but once you get the hang of it, it's not too complicated. Let's talk a little bit about outliers. In PLS, we have two models, more or less. We have a model of X, which looks similar to a PCA model. And you can do outlier detection exactly as in a PCA model. You can use your Hotelling's t-squared or leverages. You can use your residuals, the residual sum of squares, and you can look at score plots and things like that. So you can do exactly the same. And then, of course, we also have a model of Y, predicting Y from X. So we get access to standard regression diagnostics, Y predictions, validated predictions, and things like that. So you can use all these different models to look into your model and understand problematic samples, for example. And basically what we normally look for would be residual outliers, so samples that are different somehow, either in X or in Y. Or we can look for extreme samples that are maybe not of a different nature, but just extreme. So they would typically be seen in score plots or in leverage, have high leverage or high Hotelling's t-squared. Now, as I said, we're not going to talk much about this, but there's one important aspect of outlier handling. The real trick to handling outliers is to understand why the samples are different. It's not reasonable to remove a sample just because it's different. If that sample was actually fine, maybe you just had an unfortunate sampling. You had too few of that type of sample. But if you can explain your sample, then it's typically much easier to confidently handle your sample. So if you investigate and find that it's actually a measurement error, then definitely it's fine to remove that sample from the model. But on the other hand, if you find that, oh, it's actually a special occasion, these samples come from the winter production and we should have many more of those, then you shouldn't remove the sample. Instead, you should actually include more of that type. So explanation, not statistically, but technically, that's the trick. What do we want a PLS model to do for us? Well, we would like it to predict well, but how do we do that? It should actually not predict the samples we have well, but rather it should predict new samples well, and that's a different thing. Now let me give you an example. Let's say I have a small data set. I'm gonna make it here in MATLAB. It's not really important. Let's make it like this. I just want to have two small vectors that are similar, but not completely. So like this. Okay, so here I have a data set. Let's say I would like to build a regression model. Let me see if I can find this. Basic fitting. If I do a linear regression model, it looks okay. It's not perfect because there's not a perfect relation between them. Now I can make my model more complex. For example, I can do a second order polynomial instead of a linear. And I hope you can see that this line is gonna be closer to my points than the first order polynomial. So the more degrees of freedom I can use, or the more complex my model is, the better I can fit the data. And let me try and do a fourth order polynomial here. Now, this is interesting because this model is perfect. If you look, you can see that it goes through all the points. But is it going to predict well if I have a new sample here? Well, probably not, because it's overfitting. It's fitting the particular noise in my data instead of just the systematic part. And I don't want that. I don't want to add complexity to my model unless it's descriptive of new samples. So the trick is really to find out the right complexity. We don't want to fit our calibration data perfectly. That's easy. We just take enough complexity. In PLS, that would mean we just take all the components we can, and then we get a much nicer prediction of those samples. But that's not what we want. We want to have a model that describes the general part, because that's probably going to work better on future samples. So we don't want to predict our calibration data. We want to predict new data. And let's talk about how we can do that. In order to measure how well we predict, we need to have a number indicating the error. And we usually use what is called the root mean squared error. That sounds a little bit complicated, but it's actually not too bad. Let me explain what it is. So we're gonna have a y that we estimate from the PLS model and a reference, the y that we had originally. This is basically the error. Now we're gonna square that to handle sign differences and stuff like that. And we're gonna take the mean divided by the number of samples, and then we take the square root. And that's an estimate of the average error that we get. So that number is going to be in the same units as we predict. So for example, if I'm predicting in kilograms, this one is going to be in kilograms. And it's going to tell me my average prediction error. So when I predict samples, they will on average have an error corresponding to the root mean squared error. So we have to get used to saying that RMSE or root mean squared error. Sometimes we separate this error into a random part and a systematic part, the standard error and the bias. And we can approximately say that the total error, the root mean squared error, is just the bias and the standard error, squared, summed together. And you should be familiar with what these terms mean. Here, for example, we have a bias in our predictions, but the method is kind of precise. This method here is not biased, but it's also not very precise. So if we talk about predictions, we would usually see something like this. So this might be a good model. This is actually doing quite fine, but is systematically biased. And here we are not biased, but we do have a high variability around the predictions. Now, when we build the calibration models, we don't see something like this. But when you apply your model to new data, for example, from a new instrument, that's where you might sometimes see a bias. So we typically report the biases as well in models. How can we estimate the total error? Well, we can do it from the calibration data, and we would then call it RMSEC, root mean squared error of calibration. So imagine that I'm building a one component model. If I build a one component model, I can predict and I can calculate the root mean squared error. If I take more scores, for example, if I take 2 scores, I'm going to predict better. That's what we just saw in the little simulation with the polynomials. The more I add, the better I'm going to predict. And if I add another one, I'm going to predict even better. So the more components I add, the better I predict. And that means that the root mean squared error of calibration will trivially improve the more components I have. So we cannot really use this for assessing how many components to use, because it will keep improving all along, no matter what the model would do on new data. So therefore, we need a different kind of tool for assessing how well does the model predict. And one of those options is what we call the RMSEP, which is using a test set to predict our samples. So what we do is that we make a model on a calibration data set, and then we predict on completely new samples. And if you notice, the regression vector here will come from my calibration data. So it's unaffected by these values here. So when I apply my model on the test set, I do that, the results I get do not depend on my prediction Y. So I cannot overfit anymore. If I have used too many components in my PLS model, well then it's going to lead to worse predictions of my Y data. So that's a nice approach for testing how well does your model actually predict. So what you do is that you predict your test set with 1, 2, 3, 4, 5, 6 components, and you see it doesn't monotonically decrease. Once I take too many components, it's gonna get worse. So here maybe I would choose 2 or 3 components. Okay. One problem with the test set validation, let's say for example that I have a data set X and Y. Let's say I have 10 samples and I have a test set. I don't have too much money, so I have a test set of 2 samples. I don't know if you can imagine what would happen to this yellow line here. Well, basically it would become extremely uncertain. Depending on what 2 specific samples I had here, the variability of my yellow line here would be huge. So it would be very difficult to trust. It would have a high variability. So test set validation is a really nice approach if you have enough samples. And if you don't have enough samples, then you have to be a little bit careful with the test set validation. Now, that's the reason why very often we do not use test set validation, but instead we use cross validation. And the idea in cross validation is more or less to do test set validation, but do it on each sample, so to speak. So what I'm going to do is that I'm going to remove some samples, and then I'm going to build a model on the remaining ones and do test set validation. Then I'm going to build a model where I remove this part, and I'm going to predict this. So in cross validation, I leave out samples, and I do it in such a way that all samples are left out once, and I build a local model and predict. So I'm going to get a test set prediction. I'm going to get a set of predictions, but they were found by leaving out samples a little bit of the time. I can leave out 1 sample at a time or several. I just have to make sure that in the end I left out all the samples. That's what we call RMSECV for cross validation, and that will give us a different curve. And in a sense, you have used your data, you have used all your samples as a test set in cross validation. So instead of having a very small test set, you can do cross validation and use all your calibration samples as a test set. Now, there are big debates on which one is better in what scenarios, but that's not the purpose here. Both the test set and the cross-validation are routinely used, and if you are aware of sort of the pitfalls, both of them work quite fine. One thing, if you think about it, when you do cross-validation, you're building a number of different models. So let's say I have 10 samples and I leave out one sample at a time. So I'm actually doing 10 different models, but you never see those models. The only model you really use is the calibration model. So the cross-validation is just used for saying, yes, I want 4 components, but you don't actually use any of the models that were used for calculating this cross-validation. You make your calibration model based on all the samples and 4 components. So the validation is just for getting an estimate of the error that is more appropriate. It's not for actually getting the models. Okay. I want to talk a little bit about how you can use cross-validation for testing specific things. And I have an example. Let's say that we have measured some samples. Let's say we have 100 samples and they're measured in 6 different laboratories. So now I would like to use my data to build a calibration model, and I would like to show that it works on any laboratory, not just these 6. So if I have my data from lab 1, 2, 3, 4, 5, 6. So what I'm going to do then is that I'm going to do cross-validation in a special way. I'm going to do cross-validation laboratory-wise. So I'm going to leave out all these samples and make a model based on these ones. And then I predict lab 1. Then I'm going to leave out lab 2 and predict lab 2. So in the end, what I have done then with this cross-validation is to show how well do I predict a new laboratory. And I can then rightfully go out and say, well, this model actually works on all laboratories like these, not just these 6. So that would be one type of cross-validation if my aim was to show how the model works on new laboratories. Well, on the other hand, if I only am going to use this model on these 6 laboratories, then I would maybe do the opposite. Then I would maybe say, I'm going to leave out just one sample here from lab 1 because I don't want to remove all the lab information when I build my model. And that way I can show how well my model works when I use it only in these 6 laboratories. This is critical because this shows you that with the same data you can get different models, different cross-validation, different number of components, depending on what your purpose is. So you have to specify what you want the model to do in order to be able to say that this cross-validation will show me how well it does whatever I claim the model can do. We have a little question here. What about replicates? Well, the short answer is that you have to leave out replicates together. Otherwise, you're normally cheating. If I only take out one replicate but leave the other one in, then I didn't really leave out that sample. Then it's not a real test set. Okay, there's much more to be said about cross-validation. If you're using PLS Toolbox, then you can find a discussion of cross-validation and when and why to choose which one on this homepage here. The notation used for cross-validation differs a little bit from software to software. Here are some of the notations commonly used. Leave one out cross-validation is also called full cross-validation. That's when you take out one sample at a time. We don't generally do that unless we have very few samples, like 10 or 20 samples. If you have time series data, you might do something like this, contiguous blocks, so that you don't keep in samples that are right next to each other in time. We can also do Venetian blinds, depending on what type of structure we have in the data. Or if there's absolutely no structure, if the samples are just independent samples, we can do random cross-validation. And the nice thing with random cross-validation is that we can do it 2 or 3 times, and then we can actually get a view on how certain are we about our RMSE CV curve. One thing, sometimes when you're new to this, you may want to try different kinds of cross-validation and pick the nicest one. And that doesn't work because cross-validation is not changing the model actually, as we just talked about. The model will stay essentially the same. You have to do the right cross-validation. And there might be more than one right cross-validation, so you may want to try with leaving out in groups of 5 and in groups of 6. But you cannot just blindly test a lot of different cross-validation methods and then just pick the best one. You have to do an appropriate cross-validation and then use the results, whatever they are. Another thing, and this might be useful when you're trying to figure out how to decide on what type of cross-validation you want to do. Imagine that, let's say you have 1 million samples, and let's say you choose to do leave one out cross-validation. Now, can you imagine that in your huge data set, you're going to do 1 million different models, leaving out one sample? And can you imagine how little the calibration model is going to change in these 1 million samples? It's basically not going to change at all, because leaving out one sample out of 1 million doesn't change anything. So if, for example, on the other hand, you had 8 samples and you did that, so you did 8 different models, well, then these models could clearly change quite a bit when you leave out a sample. And this is also something that we're testing with cross-validation. Now, mostly people think of cross-validation as predicting new samples, but we are actually also exploring the variability that comes from what if I had sampled these samples instead of these samples. And you can only do that if you sort of shake the model. So you have to make sure you leave out a substantial part of your data in order for the model to be different. When you do cross-validation, you often look at not just your cross-validation result, but you typically would compare that to your calibration result, the RMSE-C and the RMSE-CV. And there are several reasons why you do that. Now, we know the RMSE-C is just going to improve with the number of components, but we really want to be in sort of the sweet spot where they're both similar, even though the RMSE-C is going to be better, but where they're both similar, so something like this. And for example, if you see that there's a huge difference between the two, that is indicating that we have some sort of overfitting. The model thinks that it's doing a fine job, but in reality it's not. So that might be an issue that you may want to handle somehow. Could sometimes be a case calling for some sort of variable selection. Okay, I just want to mention some rules of thumb that are often seen in the literature in different ways, and I want to explain them, but then I also want to explain what the reality behind them is. Quite often you see that people suggest using the square root of the number of samples as the number of splits in your cross-validation. Sometimes people also go for numbers like 7, 8, 10, whatever. But basically, the rationale behind this is, as we just talked about, to make sure that the model is perturbed. These local calibration models have to be perturbed. And that's what is sort of ensured a little bit by leaving out a substantial part of the samples in every cross-validation. Then another thing is that sometimes people advocate for doing different cross-validations with slight differences in the settings. Now, if you do the same cross-validation twice, you're going to get the same result. That's not going to tell you anything. But if you can slightly change your cross-validation, then you can get an idea about the uncertainty of your RMSE-CV curve. If you have time data, it's typically good to block your cross-validation segments. So you take out time chunks. In general, if you're in doubt, it's typically a good idea to use fewer components than more components. Take a look at your curve and see if you're really actually benefiting anything. Maybe there's a slight improvement, but if it costs you 5 components to get a 1% improvement in the error, maybe that's not worth it. And maybe these extra 5 components will make your model more sensitive to other things, changes in the instrument over time, for example. So often it's a good idea to use less rather than more components. Well, there's some other rules here you can take a look at if you want. And that basically includes our validation section.